Shubhodip Mondal giving a talk at our seminar, and this is his first talk on Dieudonne theory.
Right, thank you. Also, I'd like to thank the organizers for the invitation to speak. Yeah, so I guess they'll the plan is to have 2 talks, and hopefully we'll be sort of able to go over the material that was the plan. So maybe I'll start by writing down what was the plan. Okay. So the plan for the first talk is mostly to sort of try and discuss some classical aspects of Dieudonne theory. And I think towards the end, and I expect that there should be enough time for this, we'd also try and discuss a little bit about crystalline Dieudonne theory. And the plan for the second talk would be to discuss prismatic Dieudonne theory, which is sort of an analog of B in the mixed characteristic setup. And towards the end, I'll also sort of try to get to a stacky reformulation of this theory. So let me also kind of list some references. So maybe I should write smaller. So for A, I think maybe there are 2 main references that I'm following. So one is Fontaine's paper on groups p-divisible. And so Demazur lectures on p-divisible groups. And for B, for crystalline Dieudonne theory, the references this paper of Berthelot, Breen and Messing. This book called Crystalline Dieudonne theory. And for C, this prismatic Dieudonne theory, it's the references this paper of Panchus and Lebras. This paper called prismatic Dieudonne theory. And when we get to the stacky approach, I think this is based on my paper on called Dieudonne theory via homology of classifying stacks. Okay, so I think we'll get started now. So maybe for some classical motivation, I wanted to sort of start with what's called Pontryagin duality. So I'll state it in a slightly less general setup, but let me try to write down what it says. So it says that there is a, so I think I should try to, so I did something bad.
Do you want to start sharing the screen again? Or there you go. Perfect. Yeah. By the way, if you move the video out of the corner, I sort of
wanted to minimize myself. Yeah.
Yeah. If you swipe it away, I think it will work.
Okay.
So when you're back sharing the screen, if you swipe your own little icon.
Oh, got it. Thank you.
There
so
you
much.
go.
Yeah.
Perfect.
Thank you.
Yeah.
Yeah. Okay. Yeah. So there is a contravariant duality between two categories. So one is the category of compact abelian groups. So it's a topological group that's abelian and compact, and discrete abelian groups. And so this is given by this functor D, and so D is defined as, so take home from G comma S1, where S1 is a circle equipped with like the usual structure of a topological group. And then here we take continuous maps. And so in this case, actually, D square is identity. So like from the other way around, if we have a discrete abelian groups, we sort of use the same description to build the functor again. So I'm abusing the notation a little bit here, but I think it's okay. Yeah, so actually this duality also extends to like locally compact abelian groups, but I think for what I want to say, seems like restricting to the compact case is a better idea. Right, so this discrete abelian groups is also just Z modules. So let us now suppose that G is finite. It's a finite abelian group. So so in this case, map from G to S1 is also the same from just maps from Z to Q mod Z, which can be realized as like the torsion subgroup of S1. And also in this setup, we have an exact sequence. So from 0 to Z to Q mod Z. And so this Q mod Z, you can also think of this as a direct limit over all the Z mod NZs. So if we do a small long exact sequence chase, what you're gonna get is get an exact sequence from like long exact sequence of this form. And so if G is finite, so this will be 0, and this will be 0 as well. So you actually get an isomorphism between Hom G to Q mod Z with the X group here. So the reason for explaining all of this is that I think the first part, like in A, where we try to talk about classical Dieudonne theory, so just as a very, very vague kind of, this is mostly just to organize what's happening. So in part A, we'll try to write down some formula involving Hom, which is more similar to this Hom G comma Q mod Z in the context of like finite group schemes and so on. And we'll also have to replace Q mod Z by something that's reasonable for us in the setup of like finite group schemes. And in part B, which is crystalline Dieudonne theory, we'll try to write a formula involving an X group in a suitable setup as well. And then I think it was like a result of Berthelot, Breen and Messing that these two descriptions will be the same. But I think we're going to formulate this sort of later on. Okay. So basically what we learned is that if G is finite, the Pontryagin dual can be written as Hom G comma S1, and that's the same as X1 of G comma Z, if G is finite. And so I guess this is just an aside. So, I mean, one can ask, like, is there any way to sort of generalize this to the case when G is not assumed to be finite, but we only assume G to be compact? But then there are some problems about kind of taking this X1 group. So you have to sort of try and take this X1 group in a suitable sort of derived category of like locally compact abelian groups. But I think if you sort of try and formulate it the right way, it's actually possible to prove some variant of this isomorphism, even when G is not assumed to be finite. So you only assume G to be compact. But anyway, we'll not really need any of this. So let's now sort of try and get back to our main subject for this talk, which is Dieudonne theory. So for this, let K be a perfect field of characteristic P. And so the main goal for us is to, so we would like to study finite, flatness is automatic here, but we just write it. Finite group schemes G over K of P power rank. So in this context, the rank means it's the dimension of the coordinate ring of G, which will be a finite dimensional vector space by the finiteness assumption. So if, let's say if G is a discrete group, sort of viewed as a group scheme, also P power rank, so then Hom G comma S1, so it's possible to simplify this a bit further. Let's write it as Homs to QP mod ZP, and this can also be viewed as a direct limit of Z mod P to the n's. So what's about to happen is that we'll sort of define a functor that takes every finite group scheme into some abelian group with like a suitable, like some other suitable algebraic operations, which will be called the Dieudonne functor. And somehow it can be seen as an attempt of like trying to generalize this formula from Hom from G to QP mod ZP, but when G is not assumed to be discrete. So for like a general group scheme G, you'd sort of like to try and write some suitable analog of this formula.
May I ask a question? Do I understand correctly that you are tacitly assuming that all groups and group schemes are commutative unless specified otherwise?
Yeah, that's a good point. Yeah, I should have said commutative. Thank you. Yeah, actually for this talk, I think all the group schemes should be assumed to be commutative unless otherwise mentioned. Yeah. Right. So before we try to write down some kind of formula which generalizes this expression here, we'll have to sort of introduce few other group schemes that would be useful to us later on. So speaking of that, let's start with some notations or definitions. So let W denote the ring scheme over K, which is determined by. So we'll just sort of define the ring scheme in terms of its functor of points. So we just write down the functor here. So I would send an affine scheme spec B to the ring WB. So this is the ring of p-typical weak vectors. But so when we just write this expression W, it will just mean like the ring scheme. So similarly, Wn is the ring scheme of n-truncated weak vectors. So this will be determined by a similar formula that sends spec B to WNB. So this is the n-truncated weak vectors. So there are certain endomorphisms of W. So F will be a map of ring schemes, but V will just be a map of the underlying group scheme. But let me just say that map of group schemes such that FV is VF equal to P. So some of our important definitions, one is that of the Dieudonne ring. So before we go further, let me try and change the notation a little bit. So if we're working with the perfect field K, then like the Frobenius on W of K will just kind of denote it by sigma. Note the Frobenius. It's also often called the weak vector Frobenius. So then the Dieudonne ring is an associative ring. So it's the free associative ring on two symbols, F and V, which is subjected to the following relations. So PF equals P, FV equals P, and FC equals sigma C times F, and so in particular, like say that if we want to sort of consider some like left module over this Dieudonne ring, it basically means like a module over W of K with two operators F and V, which satisfies some compatibilities which are kind of enforced by the relationship quotient pi. So FV and V, F is supposed to be P, and then F is supposed to be semilinear, and so on.
Just a moment. You wrote F of C. Maybe it is just F times C.
Right. Thank you. Yeah. Right. Yeah. So F of C doesn't make any sense. Thank you. Right. Thank you. Yeah. Okay. Sort of the next definition is what's called the with covectors. So for with covectors, roughly speaking, what we're trying to do is sort of find a group schema analog of this QP mod ZP, which can be viewed as that's not good. So maybe it's good to have some examples of how this width vector behaves before we go there. So we got n truncated width vectors of FP is given by C mod P to the n. So there's one construction one does, which is sometimes called the unipotent co-width vectors. So CWU. So this is a direct limit of this system of Wn to Wn plus 1 to Wn plus 2. And the maps are induced by the Rashba, which is possible to write down once you identify the underlying set of Wn as some n tuples. So V sends it to, this is the shift, you add a 0 on the left. So, so explicitly, one can identify CWU of A, where say A is some algebra over K. So trying to write down the functor points. So as a sequence, where all the A minus I's are in A, such that 0 for all but finitely many entries. So the way this identification works is that, like here, I think we're taking this direct limit over this map V, which just adds some 0 to the left. So we always imagine that whenever we have something like this, we just automatically fill in with a lot of zeros on the left, and it somehow doesn't really matter if we add one more 0 or not. So I think this can, for example, be sort of realized as AN would be sort of viewed as being in the 0th place, and then A1 will be viewed as being in like the negative and minus 1 place, and so on. So there are some operators on this which one can define. This kind of, it can also be seen to be induced from the direct limit description, but I'm just going to write them down in terms of the formula here. So this F and V are operators on CWU. Satisfies the usual compatibilities. So I think the next construction is what's actually called the co-width vectors of A, and I think this was introduced by Fontaine. So this was introduced by Fontaine. So this CWA can somehow be seen as some kind of a completion of CWU. So how does this work? So we again have sequences like this, for which the ideal, so for which there exists an large enough R such that the ideal VR defined by nilpotent. And the group structure so there's always like a natural group structure in CWU because it was so directly defined as a direct limit along certain maps that were all group homomorphisms and so on. But the group structure on CWU extends to CWA. And so one may view CW as a formal group. And it's possible to sort of write down the underlying object that kind of pro-represents this formal group. And this is given by this description. Kind of trying to say what we said in question before. Yes, I realized that maybe this description of CW might look a little bit messy if you haven't seen it before, but the sort of the motivation is that for CWU, I hope it still seems somehow reasonable that we are really kind of trying to make a group scheme analog of this QP mod ZP. But like the resulting object is like unipotent in some sense. And if we want to do like Dieudonne theory, we are trying to study or classify all finite group schemes, which includes some of the multiplicative ones, such as mu p and so on. So, so this CWU, the unipotent version, would not be enough to study mu p and so on, which is why it's sort of really needed to work with the CWA, and I think this was introduced by Fontaine.
Yes, I think it was indeed introduced by Fontaine, and probably it was that he did this in 1977 in his asterisk.
Yeah, exactly.
It's a whole asterisk occupied by Fontaine's paper.
Yeah.
So before this work, I believe that people proceeded as follows. So, so the whole category of finite groups, finite commutative group schemes over a perfect field can be decomposed into a direct sum of three categories. One of them is étale group schemes. The other one is dual to étale, for instance, mu p or mu p to the n is dual to étale. And there are group schemes such that both they are connected and their Cartier duals are connected. Now, if you disregard, so the problem appears with in just a moment. At log. So with the dangerous part here is a group formed by group schemes which are dual to étale. A typical example is mu p. So if you disregard them, then you don't need CW you can work with the more elementary CWU. So before Fontaine's work, people did the following. They just decomposed the whole category into direct sum of the dangerous part and the non-dangerous part. And then for the non-dangerous part, they used CW. They took home to CWU. And then they treated the dangerous part separately. And so the drawback of this approach is, for instance, well, there are probably several drawbacks. For instance, if you want to work with perfect rings rather than perfect fields, then I'm afraid that you wouldn't be able to split the category into a direct sum. And probably there are other serious reasons why Fontaine introduced this notion. And it's important, but can we for a while, can some of us disregard this notion for a while? Can some of us pretend for a while that we are not interested in mu p and groups like it, and then we can just take work with CWU instead of the more sophisticated CW?
Yeah, right, absolutely. Yeah. Yeah, so maybe
you can mention the correct things, namely CW and so on. But some of us may prefer to work with the more naive CWU as a warm-up.
Right, exactly. Yeah. So I guess I'll just say that yeah, so this is the part that like I tried to write based on what like Renfrew was saying. And so this is like the dangerous part, which I sort of wrote on red, like group schemes that are infinitesimal, like local, but their Cartier dual is non-reduced. Sorry, like the Cartier dual is eta. So an example would be like mu p. And this like CW, the construction that I was mentioning, is sort of used to give like uniform treatment where we can also deal with these dangerous ones. But it's, I think, definitely like a good idea to simplify this discussion a little bit without trying to think too hard about CW versus CWU. And that would perfectly work well for this like green sort of things, which have the property that like the dual is local. So these are called the unipotent groups. Yes. So if you also make this assumption that we are only interested in unipotent groups, then it's possible to give actually a much simplifying treatment of this. So firstly, CW, so like you don't need to worry about CWU, sorry, CW. You can just work with CWU, which is just can be described very concretely as this direct limit of the WNs. And later on also there will be some simplifications. So the way I have prepared, it deals with the CW for like reasons to also that like we want to capture this mu p's and so on. But I'll try to mention whenever a simplification is possible that we don't have to use CW, and the discussion is much simpler if you use CWU. I'll try to mention them as we go along. So, but I'll still use the notation CW, but you can feel free to assume that CW and CWU are the, it would be okay to replace CW by CWU if you just work with unipotent group schemes. Okay, so note that, so in this context, there is an injective map from dk to and CW. So DK was the Dieudonne ring. I am not sure if I wrote the notation. Oh, yeah, I did. Yeah, so DK is the Dieudonne ring, and the Dieudonne ring, elements of the Dieudonne ring can be realized as endomorphisms of CW. Okay, so now we are ready to define the Dieudonne module. So define the Dieudonne module functor from the category of finite group schemes over K of P power rank to left DK module. How does this functor work? Map G to Hom G, comma CW. And this is what will be called MG. And these are all group maps, like maps, group homomorphisms. So if G is unipotent, so let me also write this down. So then MG can be described just as this more concrete formula. Okay, sort of the main theorem surrounding this is that this functor M, okay, let me call this functor M. So M from finite group schemes to left DK module, finite WK length, is an equivalence of categories.
So it's a contravariant functor. And this is why you wrote op.
Yeah.
Superscript.
Yeah. Let me write this contravariant. So actually, one of the nice things that maybe happens if you are working with CW is that it's possible to sort of write down the inverse very concretely. So you can ignore this concrete description of the inverse if you like, but I'm just writing it for, yeah. Inverse to M is given by, so we take N. So N is the Dieudonne module. And we send N to the functor that sends, let's say this is a finite dimensional K algebra. So we'll send it to Hom DK N, comma CWR continuous maps. There's a way to also put topology on CWR, basically just induced from some product topology coming from the sequence description and so on. But one can concretely write down the inverse in this case, and that's what it appears in this paper of Fontaine. But maybe what might be more important at this point is to see some examples of this Dieudonne functor in some concrete cases. So let's also introduce some other group schemes. So I can iterate the Frobenius m times, and then I get a map from Wn to Wn, and then the kernel of that can be denoted like this. So an example is that in this notation, so alpha p is just W1, 1. So the Dieudonne module for this is given by this description.
It seems that the right-hand side is the quotient of the Dieudonne ring by the left ideal generated by the powers of f and v.
Yeah.
And so the right-hand side depends on m and n, and the right-hand, as these numbers vary, you get a projective system.
Right.
And you're talking about contravariant Dieudonne equivalence. So this means that these group schemes W, M, N should form an inductive system with respect to M and N.
Mm-hmm.
And indeed, they form an inductive system with respect to M because we are taking the kernel of f to the m. And as m grows, the kernel becomes bigger and bigger. Now, why do we get an inductive system with respect to n? Probably this is, so how do you embed Wn into Wn plus 1?
This is the Verschiebung, I think, that we add is 0.
Using the operator v.
Mm-hmm.
I see.
Somehow, I think there should be a very precise statement along this line that you're saying that this inductive system I get from Wn and m and should somehow form generators in a suitable sense for all these local group schemes that maybe I'm afraid I'm not able to make properly right now, but
something, Shubhodip?
Yeah,
so
sure.
This equivalence also exact?
Sorry?
So is this equivalence also exact?
Yeah, right. Maybe I should have said that the equivalence is exact for the exact category structure on both sides. Yeah, thank you.
Thanks.
But actually, if you have two abelian categories, then an equivalence between them is automatically exact because the notion in an abelian category, the notion of exact sequence is defined in terms of the maybe you need the words to say that your equivalence is additive, but maybe even this is automatic. So probably exactness is formula follows from the rest,
right?
Because it's an anti-equivalence.
Right. Yeah.
And can I ask a question as well?
Yeah, of course.
So does your formula for the inverse map mean that sort of the addition on any group scheme is given by some sort of like Witt polynomials?
Yes, of course. As Shubhodip told us that the Witt polynomials are everywhere here because the group law on CWU is defined. Well, you need maybe not. It depends on what you mean by Witt polynomials. I would say that the mysterious Witt formulas are always around here because you need them to define the group law on Wn, and then CWU is defined to be the inductive limit. And so there are these mysterious width formulas are, we don't write them explicitly, but they are here. And then to define the group law on the whole CW, so Shubhodip didn't explain the details, but it's believable that everything extends. So this is a theorem. My understanding is that it extends. The only thing that you need here is that everything is homogeneous. So the a thing to keep in mind is that the group scheme W receives the ring scheme. We have a map from GM to the multiplicative group of the ring W. The map is given by the Teichmuller embedding. And because of this, the multiplicative group acts on W. And because of this, all the formulas are homogeneous in an appropriate sense. So you have to be careful to assign the degree to each correctly. You have to assign the degrees to each coordinate in a correct way. And then if you take all this in account, then you see that our group law indeed extends from CWU to CW. So I would say that you have the magic of width vectors. The magic is that certain polynomials which a priori have rational coefficients, in fact, are polynomials over the integrals. We tried to never write these polynomials explicitly, but they are behind the, they are always behind the C. So,
yeah, I think maybe there's one like toy case that might also be worth explaining is back in the story of this like contravariant duality. So it gives an equivalence between discrete abelian groups and compact topological abelian group. And so any discrete abelian group, you can resolve it as a two-term complex of free Z modules, like free abelian groups. And under this equivalence, this actually gives some kind of a structure theorem for all compact topological abelian group, in the sense that inside a suitable derived category of locally compact abelian groups, you can also realize them as a two-term complex of some infinite products of S1s. So something similar can also be said in this finite group scheme story by means of the Dieudonne theory, that basically, like in some sense, the equations going behind width vectors determine the group equations of every finite commutative group scheme. But yeah. Okay, so maybe let me just write one more example. This is mu p to the n. And so these two are actually just like Cartier duals, and it's also nice to see the symmetry in the formula of the Dieudonne modules. Okay, maybe let me write down one like basic property of the Dieudonne functor. So in principle, this gives an equivalence. So every property about finite group schemes should admit a translation in terms of the Dieudonne module. So let me just write one such thing, is that if you wanted to find the rank of G, that would just be the length of WK, sorry, MG as a WK module. Okay. So in some sense, this finishes our discussion of part A. And so we'll move on to like part B. And from now onwards, I think...
just a moment.
Yeah.
At some point, we need a break. Let's say a 5 minutes break. The question is, when would be the logical time for it? Is it now? Or...
Yeah, I think this is a great time for a break. Yeah.
Okay. So now we take a 5 minutes break, and then we continue with part B.
Okay, yeah, so let's continue. So part B is about crystalline Dieudonne theory. And maybe some of the motivations for studying this could be that, from the perspective of our talk, is that if you want a uniform description of the Dieudonne module as we gave, so you need to think about CW. So maybe CW is complicated. And the story explained so far works over fields, but one can wonder what happens over slightly more general base rings. So about more general base rings, we would say more in the next talk, but right now I'm just like mentioning this as like some kind of motivating questions to keep in mind. So what this crystalline Dieudonne theory is about is, very roughly speaking, use the crystalline site to study group schemes. And going back to, just as a reminder, going back to the contravariant duality story, what we are aiming for is to be able to sort of write down a formula like this in a suitable category. So let's say K is a perfect field, and WK, P, and gamma is a divide power structure on the ideal P inside W of K. So what this means, like, I guess I'm not formally defining it, but I just want to say that just means that these elements like P to the N over N factorial will be sort of considered as maybe a divided power of P. And this is automatically in W of K. So like this makes sense as an element of W of K, even though I'm dividing it by some denominator N factorial. Can be checked by comparing the powers of P that appears in the numerator and denominator. So just before we go further, I want to also say that like one of the concrete constructions that one can do in the presence of, like, say, divided powers is the following: that say that I have a ring A and I have an ideal I and a divided power structure gamma, and also suppose that A is p-adically complete. So let's say if I pick an element x in I, just log 1 plus x is given by this formula, and can be written again as so because of these numbers appearing here, this actually makes sense and it converges periodically. So we get a well-defined element of A. So I think these sort of constructions are kind of like an important feature for us in something that we will get to later on. Okay, so let me start by defining the crystalline site. Give a category, those objects. So I think I'll be a little bit vague while explaining this, but delta. So what does this mean? So, oh, by the way, this is also what's called maybe the big crystalline site. So this is a U is a scheme over K, and this is a scheme over W of K, where P is locally nilpotent. This map is a closed immersion for WK. This delta means that we have divided powers of the ideal sheaf of the closed immersion I. So ideal shape of O of T. So we often also add the condition that like I is supposed to be, sorry, that T is supposed to be some nilpotent thickening of I, but this is actually automatic in our setup because you work where P is like locally nilpotent and we also have divided power. So there's one calculation one can do that gives you that condition automatically. And so this category can be made into a Grothendieck site. By equipping it with, say, the Zariski topology. The choice of the topology is not, like the constructions will do, it's not really sensitive to the choice of topology. One can choose the Ital topology, for example, as well. So some other related constructions here. It's that the crystalline site has a natural structure sheaf, a sheaf of rings, which is determined by, okay, maybe I'll write this. P gamma of T comma O of T. And this is also equipped with a natural ideal sheaf. And one that has divide powers as well, more or less by construction.
When you say Zariski topology, you mean with respect to Zariski covers of T?
Exactly, yeah,
Okay.
right, right. Thank you. On U, it's just a pullback of what's happening at the level of T.
So the crystalline site that you are defining is usually called the big crystalline site.
Right.
So we are more accustomed to the small crystalline site, the small ethyl site, and so on. But sometimes it's convenient to work with the big ones.
Yeah. Especially in this case, where we're interested in this formula of the X group, it will be really quite important for us to.
Yeah. Anyway, it will be pretty clear that the small crystalline site is incorrect here for our purposes. The fact that the big one is good. It's not so obvious, but the fact that the small one is bad will probably be obvious.
So we take kernel of this. So when we have a big site, there are some constructions that one can do, which I'll try to explain. So let X be a scheme or a group scheme. So maybe it's better to say scheme or group scheme over K. Then we can define some construction. So here we just map it to the u-valued points of X and do not worry about the thickening really. So this is a sheaf of groups on so we also define crystalline cohomology since we have defined the crystalline site. So I'm defining it by the formula. So to see this with maybe, I don't know, the more usual definitions involving the small crystalline site of X, I think one needs some comparison between the cohomology of big sites and small sites and so on.
Just a moment, what is X here?
Sorry. Sorry. Yeah.
What kind of object is it?
Right. Yeah. Right. So sorry. So let X be a scheme over K, and I think some of the things I wrote maybe doesn't appear very clearly in my equation. So this is really the X underlined, which can be viewed as a sheaf on the crystalline site, and then ZX sort of takes the free abelian group on that. And so then these are both sheaf of abelian groups, and I can take their R home inside the derived category of abelian sheaves in the whatever duality. We'll actually not need this today, but maybe in the next.
So usually our gamma cris of X is defined in terms of the small crystalline site of X.
Right.
But you are saying that for certain tautological reasons, which we don't have to understand right away, that this is equivalent to your definition in terms of the big crystalline site.
Right. Yeah. Right. So sort of the main result here that we are headed towards is this result of Berthelot, Breen, Messing says that, well, in the previous setup, but maybe I'll recall that G be a finite p power rank group scheme over A. So the result is that mg after the Frobenius pullback, which is kind of harmless because sigma is the map from WK to WK, it's an isomorphism because K is perfect. This can be given by a X group. So for the rest of the talk, my plan was to give a sketch of how one proves this. But maybe before going there, because I'm not sure how... Yeah, so this is the proof that appears in Berthelot, Breen and Messing. I think it's a little bit involved. So maybe I'll just try to make some preliminary remarks. Yeah, sorry.
And can you recover with vectors in this manner, not only the Dieudonne model, but, well, for finite group scheme, but the with vectors themselves using crystalline topology?
Yes, so is the question, can I get the width vector of the coordinate ring of G?
Yes, just a schema with vectors or CW maybe.
So if I have a scheme or sorry, so like say if I have a group scheme already, like say maybe W, I can always I can always take W underline by doing this construction here, that something like this, and we can also do this to CW, but this only gives me a sheaf of abelian groups without really having any sensitivity to like the thickenings. So I guess maybe what I'm saying is that I don't have a better answer than this. That like say if I have the width group scheme, I can always take this W underline, which is given by sending this to the U-value points of W, but
usual W, not underline.
Oh, sorry. Yeah, right. So thank you. Yeah, this is definitely one construction that one can make, and we'll be doing similar construction using the CW, actually. Yeah. But I guess what one feels is that maybe it's not really simplifying the group scheme in any way. Like it's not giving us anything more that we can say or do about the group scheme W. But with finite group scheme G, though, yeah, one is able to get the Dieudonne module by some kind of a formula for which takes values in the crystalline side. So yes, I'm not sure what more one could say about the width group scheme W.
Thank you.
But we'll be definitely using CW in this manner, and that will be an important ingredient in the proof when we get to that. Okay.
And, why should we happy? Why should we be happy with this mysterious theorem? So here, in the classical Dieudonne theory, we are taking homes between group schemes, and at least the definitions of what we're doing of the home is elementary, understandable, and so on. Now, the theorem that you formulated says that this can be, this is the same as taking X on something, on some huge site. So my naive question is, why should we be happy with this? So
Yeah.
this was the theorem from, well, the proof is given by Berthelot and Breen and Messing, but probably originally it was suggested maybe as a conjecture by Grothendieck, and probably he had good reasons to suggest this approach.
Could I ask, just as a continuation, does it mean, I mean, in parallel with the picture of Pontryagin duality, does it mean that the sheaf or crease in some sense is the fundamental group of CW? In some sense, it's like Z played the role of fundamental group of the circle in this description of Pontryagin duality using X1. And does this thing mean that you have also, in some sense, O crease is the fundamental group of a CW? I mean, just as a continuation of what Volodya asked.
Yeah, I think this is a great question. So let me just like try and take some time to add some remarks and try to say like the best of what I can. So I guess I'm going in the reverse order of the questions in the order to receive. But first, so I guess the second question was, is O-crease somehow the fundamental group of CW? In some sense. And it's definitely an interesting question. So let me try to, like in analogy with the Pontryagin duality case, let's try to see the analogies that we are proposing. And yeah, so here once we have Z, one, here we have, sorry, S1. And somehow the analogies seem to be that, at least the way the harms and the X go, here I have O-crease, and here I have CW. Okay, I think it seems difficult to answer this question directly now. So I think I will try to say something about like Renfrew's question. So I think that question was, why is this X1G, O-crease? Why is this X group like interesting, or like what's the motivation behind this? So I think this will be something that I'll try to explain in the second talk in the part D. So there's also another formula for this, which is given in my paper, which is that this H2 crisp BG, this is isomorphic to X1 of G O-crisp. So I'll try to explain a proof of this in the next talk. But here I think what we are saying is that G sort of appears as pi1 of BG. And I think this can be, so one can try to prove this directly. So then I think sort of the formula becomes that H2 crisp BG And sorry, so what I should do here is that I think I should add, sorry, just a moment. My list is written badly. So here I have Pocrace, here I have CW, here I have X1, G, Pocrace. And here I have X1, G, Z. So now if we also assume that G is finite, one can actually, so I was planning to say this in the next talk, but maybe now it's a good time. So one can use the universal coefficient theorem to prove that this X1 group and the singular cohomology of BG are the same. And the analogy here is that this is the same as crystalline cohomology of BG. So I guess for Drinkel's question, which was this like X1 group, I guess what I want to say is that maybe a better reformulation of the X1 group is really in terms of the second crystalline cohomology of BG, which is completely compatible with the picture on the Pontryagin duality side. So yes, this side is the Pontryagin duality. And this is the side of Dieudonne theory.
So the definition of X, the X group is computed inside some huge topos. It's a big crystalline topos. Your description as the crystalline cohomology of BG looks more elementary and it looks nicer, and probably it is nice. But in some sense, it also involves some huge topos, because if we ask ourselves what is BG, then we probably have to have to say that BG is a sheaf of groupoids on the category of schemes and so on. So in some sense, this huge topos doesn't disappear in your formulation, but I agree that your formulation gives more understanding, at least. Now, but I do understand correctly that Grothendieck's original motivation was to develop a kind of Dieudonne theory, for instance, for non-perfect fields, or more generally, well, for more or less arbitrary algebras over Fp. For instance, smooth algebras. And then he realized and explained to other people that in this case, in addition to p-linear algebra, to things in the spirit of p-linear algebra, you also get a connection. Well, you had a vector bundle with an integrable connection, and the crystalline side is the language suggested by Grothendieck to talk about vector bundles with connections in the right way. Now, do I understand correctly that this description of this X group, my understanding is that the advantage of this description of the Dieudonne model in terms of X, the main advantage is that that it can be generalized to group schemes over, for instance, over non-perfect fields or over smooth algebras.
Yeah, right. Yeah, so this X group, one advantage, I guess this is the advantage maybe of working in the crystalline site in general. So this is maybe something that's valid for both X1 and H2 Chris. But the point is that in the X formula, it's easy to replace the big X by Sheafy X. And then often one gets a crystal. And this gives the kind of generalization along the lines that you were saying. And I think we'll say more about this kind of things in the next talk. So I also wanted to say a little bit about this pi1 of CW and O-Chris, but which is not really an answer, but maybe just to sort of clarify a little bit. For us, I think Z appears in like two ways. One, so this is the story in the Pontryagin duality. So, okay, so this is a Z. And I'll try to explain what I mean by the Z. So like the red G is the Z here. So this Z, I think of it as the choice of the coefficient for which I'm taking the cohomology. And the other Z, this Z for me, so there's another Z here, which comes in the story of Pontryagin duality. That Z actually comes as Hom from S1 to S1 as the Pontryagin dual of S1. So it's the endomorphisms of S1. Doesn't really appear as pi1 of S1 there. So here, the analog for the other Z would be the Dieudonne ring itself. This actually appears in Fontaine's paper that after a periodic completion of the Dieudonne ring, this is the same as endomorphisms of CW with respect to appropriate topology. So I think unfortunately I'm avoiding the question, but I feel like the Z's show up in slightly different ways. So here, there's one Z that in Pontryagin duality, compact abelian groups correspond to Z modules. There the Z shows up because of endomorphism of S1. The analog of that would be how the Dieudonne ring appears as endomorphism of CW under the analogy of S1 and CW. And the O-Chris enters really as just choice of the coefficient for the cohomology Z, like the coefficients.
Thank you.
Okay, so some other remarks before entering the proof, because I guess I'm going to sketch the proof anyway, so maybe it's better to pause. This X group and Berthelot, Breen and Messing first, before proving this, they do some computations. For example, in the case of an abelian variety. So if A is an abelian variety, then the proof that X1 is the same as crystalline cohomology. So this weird X group still is computable in the case of abelian varieties. And in general, there's a result of Renault which says that, like Zariski locally, for fields, it doesn't matter. Every finite group scheme like this can be resolved by a two-term complex of abelian varieties. So if you have a nice answer for abelian varieties, this somehow says that looking at X group like this is not completely hopeless, that it will give us something nice. It can at least give us something nice. So there are computations one can do that already shows that this side isn't so bad, even before one proves the equivalence with the Dieudonne modules, which is the classical story. And so also I think the formula I wrote down here, this also works for abelian varieties. So you'd also get that this is H2 cris B of A, and these two are the same. H2 cris BA is same as H1 cris of A. I'll try to explain this kind of things more maybe in the next talk. Maybe a final remark. Okay, not sure about that. But further remark is that so I think if G is unipotent, so I'm making the simplifying assumption that CW and CWU, okay, so sorry, meaning that I will work with like CWU, which is so if G is unipotent, so one can try to see directly that H2 cris BG is the same as MG. So I think it can work outside the unipotent case as well by using some duality or something, but I want to only say the unipotent case because of slightly simpler things that one can say in this case. So maybe point one here is that, so there was some discussion about big sites and so on, but if you are interested in computing crystalline cohomology, big sites sites are not the only way. You can also compute crystalline cohomology by maybe Luce's theory of de Rham-Witt complexes. So one can also approach crystalline cohomology by de Rham-Witt complexes. So there are additional methods available to compute these crystalline cohomology groups. And in that context, there's an exact sequence that appears in Luce's paper that I found quite helpful. And I think it's a bit easier if you're only interested in a unipotent case. One could use H2 cris BG instead and then try to do something simpler, which is that, so here we have the de Rham-Witt complex. And here we have the unipotent co-Witt vectors. And there's a natural exact triangle here in this setup. I have to write what that is. So that's given by a direct limit of a somewhat twisted version. Okay, this twist, we'll see what it really does, but I should define what these things are. Okay, I'm only going to define what the twist means. So let's say the de Rham-Witt complex looks like this. This complex, the way we're defining, is that everything here remains the same. We'll only change the first differential here. And this works out to give a commutative diagram. So for that, we use that f dv is d again. So then note that we always have an exact sequence of this form. This gives, so whatever I wrote here, it gives me the exact triangle that I wanted. So I'm being slightly sloppy here because one needs to do it properly for that step that I'm about to write down. But this exact triangles always gives me maps from, there's always a boundary map now. From this, sorry, map from this to hi plus 1. And this is just crystalline cohomology by the Dirac-Witten crystalline comparison. So let's try to apply this for x equals bg and I equals 1. So h1 bg comma cwu, it's a map to h2 bg. And this is possible to prove directly. This is something happens in group cohomology as well. It's not that bad. So this gives the map, and then one can try to check that this is an isomorphism. It'll not be so bad. So in this case, one can also directly prove the injectivity of this map, and then if you can compute H2 BG in some case, there's several ways to argue. Yeah. So
just a moment. So is it the approach based on Dirac-Witten written in your paper?
Yes, this is not written in my paper. So this sort of occurred to me while trying to prepare for this talk, and the details are also not like thought out yet, but it seems like using the Dirac-Witten approach, one gets a simpler treatment, definitely for the unipotent case.
Yes, this is very good news. But so you're saying that in your paper it's hopeless to find the words about Dirac-Witten, and it's hopeless to find them anywhere in the public domain, correct?
Yeah, I think the Dirac-Witten approach to computing H2 Cris BG, it doesn't appear in my paper, but it seems like
maybe you have some secret notes in which the Dirac-Witten approach is written.
Yeah, I guess I'll try to write this and then.
So they appear in the notes that are not yet written.
Mm-hmm.
Well, maybe in the future, when you write them up, it would help us if you could share it with me. Then I can, for instance, and then I could send them to the seminar participants, or you can place it on your web page. Something like this.
Yeah.
Excuse me, but am I right that this exact sequence which you attribute to Illusi is, again, it's parallel in the story with contravariant duality to exact sequence Z goes to R, goes to the circle. So the role of R, of the universal covering of the circle, plays this weird inductive limit by V of the twist, well, this W omega X of M.
Yeah, I think this is kind of like in crystalline analog of this, but actually this formula can be found in Illusi's paper towards the end.
In this huge École Normale paper.
I think in this paper called maybe Dirac-Witten complex and crystalline cohomology.
Yes, it was the big one.
Yeah,
not digest, but
yeah. So there Ilusi talks about this exact triangle, which gives he also gives construction of this map that exists, and it seems that one can use that to sort of understand this CW inside crystalline cohomology in a fairly general setup. And yeah, so it's also analogous to the sequence of Z, R, and S1 you said. And I guess that also kind of shows that maybe the Z there really appears as coefficient of the cohomology theory, kind of like what happens in the Dirac-Witt setup. That we get the Dirac-Witt complex there on the left.
Also, excuse me, well, this, well, when you pass from usual Dirac-Witt to this strange thing in the middle of the exact sequence, you basically touch only the first component of the Dirac-Witt complex, the Witt vectors themselves.
Yeah.
Yes, you change the rest. The rest stays the same. Yeah, and does it come from some certain maybe extension of CW by W or something like this? I mean, what? How much is actual Dirac-Witt comes here, or it's only essentially playing with vectors and then applying something very, very standard?
Yeah, exactly. Yeah, I think that's a great question. I don't have a direct answer, but maybe this is a good preview of the sketch of the proof of Berthelot, Breen and Messing, where they do something more similar to, I think, what you were saying. And maybe it'll now, I think we can move to that part. So
sorry.
Yeah, no problem. Proof due to Berthelot, Breen, Messing. So basically, I guess since we had all these remarks, it's maybe good for motivation. What they're doing is trying to write this down in the crystalline site. More generally also for CW, not just CWU. But the whole thing will happen in crystalline site. I will write them down. I think linearly it's possible to follow this, but I should say I didn't understand what was going on that well. The Dirac-Witt part seemed simpler, but in the crystalline site, we'll see. Okay, so sketch of proof. So we will construct an extension in the crystalline site of this form. So this is a subsheaf of CW. So maybe one should say it's not directly CW that's appearing, but a subsheaf. But I think this is also larger than the unipotent Witt vector. So it's kind of in between Witt vectors and the CW, but for our purpose, this will not matter. And that's something what they show as well, that for our purpose, it does not really matter. So why do we want this? The reason we want this is because then we will get a map from G CW to, because we want a map like this. And this exact sequence will give us that map. Okay. So some general understanding of the coit vectors is that for any ring T, the Verschiebung map is actually surjective, the way it was defined for coit vectors, and the kernel is given by T. So we can apply this directly to the crystalline site, to the sheaf of rings ochris. Sure. Okay, and this is where the divided powers seem to play an important role. So there's a natural map, but there's also another map S, which kind of, okay, this is the natural map. Gives a commutative diagram like this. So something that we have to do now is to define this so this will be given by a transcendental formula, but because of divided powers and p-completeness, it all makes sense. So, okay, let me use one kind of notation. Anyway, this formula, one checks that S is additive, and then the extension is obtained in terms of these maps.
Just a moment, and what you wrote with these factorials and so on, this is something like logarithm.
Something like logarithm, exactly, yeah.
Yes.
But only the p to the nth powers appear, though. Yeah. I think maybe it's this Artin has logarithm exponential. There's something that looks like this. Maybe it's the p logarithm, something like that. Sorry. Yeah, but it is like the logarithm, yeah. So we have this exact sequence. This is what you're going to be using. So now it's the time to give these things names. So that will be our E. And our CWK is this. So this gives us the sort of extension we wanted.
Excuse me, I missed something easy. So how do you embed W of K into CWK? So you write CWK mod W of K, but
sorry. Yeah, no, that's just bad notation. Sorry. This is to show that it's like happening in the crystalline site. It's just something I define in the crystalline site. Sorry. Sorry. That's just the notation. Yeah. I hope I didn't leave it anywhere else. Looks okay.
It's so you're so this you're just saying that you work in the crystalline site, in the big crystalline site of K, viewed as an algebra over W of K. And so it's not, my understanding of syntaxes in your formula was incorrect. This is.
Yes, sorry, maybe that was not best choice for me. Yeah, but this like CW ocris is literally just CW being applied to the ring object ocris, and the formula makes sense for ideals as well. And then this quantity is just the quotient, and this is just a naming for it. So given this exact sequence, we get a map like this. And then one needs to do some argument, I think, to show that this is the thing I want. And I haven't been very careful about WK linearity, but I think if one were to be, then we would get the right formula should, involve the Frobenius twist of MG. Yeah, so the small remark about the Frobenius twist is that I mean it's somehow kind of interesting that this X group G ocris is the same as H2 crystalline PG. This is naturally isomorphic to MG to the Frobenius pullback, but if you just want MG, it's actually naturally the prismatic homology group. So this somehow gives an analog for the exact triangle that we had involving the Dirac-Muit complex in the crystalline site, but I guess it's a little bit. Yes, we don't really get CW. We work with some kind of intermediate between CWU and CW, which is what we are calling this object. It's an intermediate between the two, but for our purposes, this doesn't seem to matter. And the extension is really constructed for this intermediate. Okay, yeah, so I think maybe another thing one could say from here is that, so the kernel of this map here is given by form from G into E, and this one can argue that in our setup, this is 0. So one gets an injective map. And then once one has an injective map, it's possible to estimate the length of this side, and then some argument will say that this injective map must be an isomorphism. Maybe it's fair to say that in some sense one really cares about having some extension which kind of produces this natural map. And once one has the natural map, it's okay, one also wants it to be injective, but sorry, I guess the point I was trying to say that I think in the paper of Berthelot, Breen and Messing, not much is said about the cohomology of this extension E, for example. And in Ilusi also, I think not much is said about cohomology of this, like the middle term here. But in special scenarios, I think for example, if we're working with stacks such as BG, it's possible to argue directly that H1 of that is 0. Like I think it's possible to prove some small vanishings as one needs, but in general, much doesn't seem that much was said about cohomology of that. So think in the next talk, I will say more about stacks. And so I think we discuss this isomorphism, PBM, Berthelot, Breen and Messing, with X1. So in the next one, we will say more about how to prove this. And what I was trying to sketch earlier is that in the case when G is unipotent, one can, maybe let me give this isomorphism a name, maybe theta. We can prove theta using Durham-Witt complex, which is a bit simpler, I think, in this case. So so in principle, if G is unipotent, one gets a proof of PBM by adding theta and top 2 together. That doesn't use the explicit constructions in the big crystalline site. So this will be maybe one of the things that happens, maybe the part D. And in part C for the next talk, maybe it's the thing that Drinful was also mentioning, is that so it's possible to replace this by Schiff-Yext and study this as a crystal and say also in the case when G is p-divisible. And this is what something we'll talk about, which extends Dieudonne theory to more general base rings. And in this part, we'll also say some stuff about prismatic Dieudonne theory. Okay. So I think I'll stop here. Thank you.
Thank you.
Will you share the notes?
Yeah, sure.
Yes. Okay. So please send them. Shortly before your talk, I sent you an email with 2 email addresses.
Right.
Can you please send the notes to me and to the 2 email addresses mentioned in my email?
Yeah, sure.
If you wish, you can also send them to Sasha, but Sasha can get them from me also.
Okay.
Okay. Now, here is a question, kind of, well, the problem for me is that the paper by Berthelot, Breen and Messing is long. Also, now my hope is that, well, the modern approach to crystalline cohomology based on prismatic theory, especially on the Stacky approach to it, is in some sense easier than the original approach based on the crystalline site and so on. So the question is there now, does your work give us a way to bypass Berthelot, Breen, Messing? So is there a way not, maybe reading Berthelot, Breen, Messing is instructive, but our time is limited. So is there a way not to read it nowadays?
Yeah, so it seems like if in the unipotent case, sorry, at least in the unipotent case, one gets I think one gets this isomorphism without having to do I think the whole proof that I was explaining earlier about this concrete things about the crystalline site. I think at least in the unipotent case, one can replace them by trying to compute H2 crisp BG using the Derham-Witt complex. And then one gets this theta directly, that one directly gets H2 crisp BG in terms of, sorry, by trying to directly compute with the Derham-Witt complex. And so in talk 2, we will actually show that this isomorphism holds for like very formal reasons. For example, it just really depends on the fact that pi1 of BG is G in some sense. So it, at least in the unipotent case, it seems like one can avoid the proof that I was sketching earlier. And I guess the case you're calling the dangerous case, I think the hope is that the dangerous case can also be dealt with like duality, but I guess I haven't really thought about that part yet. But in principle, it seems like the dangerous part should also, one should be able to deal that with duality as well. So once one proves theta for the unipotent case by duality, it should extend to all the finite group scheme case. So then I think it should be possible to I think bypass the sketch of this proof and many other ingredients that maybe that goes in here.
Yes. So my understanding is that maybe it will be possible in the future. It's almost possible now, assuming that we are interested in perfect fields.
Yeah.
I'm not so sure that it's already possible if we are interested in, for instance, in non-perfect fields. Then maybe this is for the future. Yes.
Yeah, but I guess in general, like as you're saying, one can take the Schiff group, but instead of this H2 crisp BG, one can also take the R2 Floa star or something like that. Sorry, what am I saying? Oh, sorry. Sorry, say that say that G is over, I don't know, some base spoof R, and then we get a map from BG to sorry, spoof R, and then one can approach, one can apply this like stacky approach, and then get this map F prism, and then seems that F prism, sorry. So this is now naturally an object in DQC. Yeah, so I guess some construction like that one can pretty much do directly by using the stacky approach.
Mm-hmm.
But I think it's more or less the same as writing down the Schiff group as well.
Yes. You're saying, I think you're saying the following. I think you are saying that the whole point of Berthelot, Breen, Messing is to compare
Yeah.
Compare Dieudonne's answer to an answer in terms of the X group. And in the case of an arbitrary base, we don't have Dieudonne's answer as a home. And therefore, in some sense, my question doesn't make sense, since there is no question about, it's not clear how to pose, to compare. So indeed, the stack approach and so on allows you to write some kind of answer, but unless the base is the spect of a perfect field or maybe a perfect ring, we don't know, we don't have another answer with which we could compare. At least it's not clear. Okay. Are there other questions or comments?
Yeah, I have one small question. So I probably missed that. But did you say how to show this surjectivity of the final isomorphism?
Oh, yeah, it don't really show the surjectivity. You try to sort of estimate the length of the target, and then you prove that the length is less than the length of the Dieudonne module. So yeah, so you don't have to do it with the surjectivity, I think.
I see.
And this kind of length estimations are possible to do by embedding G in abelian varieties and so on. And
I see, thanks.
yeah, so I guess maybe it's a good question. I guess maybe it just brings me back to the fact I was saying that I don't know a lot about the higher cohomology of this middle sheaf E over there. So, and that's also not something that Berthelot, Breen and Messing seem to wanted to get into.
I wanted to ask about this map S. Like, is there some motivation for it? Like, can one view this geometrically, or does it fit into some bigger picture? Or
you mean the map S? Sorry, I think.
Yes, so the map at the bottom of the screen right now. This thing involving like logarithms.
Oh, that's a good question. I don't have a good answer to this. There are some very concrete calculations one can do. If you apply this, so the sequence here, what am I doing? So like the sequence here, so Ocris gives me some algebra. Say that I take that to be the ring of Witt vectors or something. Then one can try to see what this sequence says. And there are some explicit ways to sort of address it. Okay, maybe I'll just try to write something very briefly. So sorry, actually let me, so I don't think I'm able to say the thing I wanted to say. Sorry, I think in short, I guess I don't know of a very good example, but I think as in like sometimes you can try to apply this to like specific Ocris, and I think it agrees with the sorry, maybe I wanted to say this. So in general, we have this W of A, and we have this CW of A, and something like that. Oh, sorry, actually, never mind. Yeah, so I think in general you have some of these exact sequences, and maybe you can try to make this sequence explicit in some cases. Sorry, where did that? Yeah, you can try to make it explicit in some cases and maybe try to see what it's saying concretely. But I guess I don't have a very good answer. Sorry.
Thank you.
Other questions or comments? Let us thank the speaker again.